I'm Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up on collisions with oscillators. In this video, we're going to talk about collisions and spring oscillators. And we're going to use conservation momentum amongst other things like conservation of energy. So let's look at three different scenarios. So we've got this first oscillator. As it oscillates, we're going to drop the box on top of the oscillator as the spring is stretched at its max. The two continue to oscillate together. Let's look at a second scenario where we've got the spring that is oscillating, and this time we're going to drop the box when it reaches at equilibrium and moving to the right. And then the boxes continue to oscillate, and we'll answer a couple questions about those two situations. Then we're going to have a box that is moving, colliding with another box that is attached to a spring. The spring is at equilibrium, and then as they collide, they stick together and continue to oscillate. So looking at scenario one, we have the oscillator as it oscillates, and we're going to drop the box when the spring is stretched the most, and then the boxes continue to oscillate. So we're going to assign some variables, and all questions are going to be solved in terms of these symbols. So each box has a mass of m, the spring's going to have a spring constant of k, and the spring's going to be stretched. And as the two oscillate, we're going to answer these questions. How does this affect the amplitude of the oscillator? Two, how does the dropping a box of equal mass impact the period of oscillation? And three, what is the effect of the speed of the oscillator as it moves through equilibrium? So let's look at the first question. So how does this affect the amplitude of the oscillator? So if we delve into this a little bit, because the spring is completely stretched when the mass is dropped on top of the oscillator, that means the amplitude is not going to be impacted. And that's because the spring energy is unaffected by the new mass being dropped. So we only have momentum in the vertical direction of the box moving, because at the moment that the spring is stretched its most, that means the box that is oscillating doesn't have a horizontal momentum. And that vertical momentum is not going to be conserved because the floor or the box not being able to move vertically is going to be an outside force causing that momentum to stop. So that means the only thing that's going to happen is the velocity is zero, so we'd have to use conservation of energy. So how does dropping the box of equal mass impact the period of oscillation? Well, we know from the period equation that the mass and spring constant are the only things that affect the oscillator. So we can look at the spring equation, and we know that period is proportional to the square root of mass, because period is on one side and mass is on the other under the square root. So that means if you double the mass, that means the period is going to be the square root of 2 times greater. It's going to take longer to oscillate because you have the same spring force pulling twice as much mass. So it means if the period was 1.5 seconds with one mass, it's not going to be 2.12 seconds with two masses, or 1.5 times the square root of 2 seconds. So now the third question is going to be a little bit longer to answer this one. So what is the effect on the speed of the oscillator as it moves through equilibrium? Well, because the speed of the oscillator at the moment the box is dropped is zero, we don't have any momentum horizontally, so we can't use conservation of momentum. But we know the spring is stretched and there's energy in the system. So what we're going to do is we're going to use conservation of energy, and we're going to draw an energy bar chart for this situation. So you can see the energy bar chart. We have stored spring energy at the moment the box is dropped. The spring transfers energy to the box, and when it goes to equilibrium, that means we have all kinetic energy at the moment that the box is traveling through equilibrium. So if we use our conservation equation, stored spring energy equals kinetic energy, we can substitute the equations for each type of energy. And solving for the speed, we get the speed is equal to the amplitude times the square root of k divided by m. So what is the effect of the speed of the oscillator as it moves through equilibrium? Well, we've doubled the mass. So if we look at this equation a little bit further, we see that speed is on one side and mass is on the other under the square root, but it's in the denominator. So as mass increases, velocity is going to decrease, but it's not an inverse relationship because the mass is under a square root. So doubling the mass means that the velocity is going to be decreased by the square root of 2. So an example, if it was 2.5 meters per second, it's now going to be slower, 1.77 or 2.5 divided by the square root of 2. And the reason for that is we have the same force pulling more mass, which is not going to allow it to accelerate as great once it gets to equilibrium, if you think in terms of Newton's second law. So more mass means the same force causes less acceleration, which means a slower velocity. So let's look at scenario two, where we have a box that's dropped and it lands at equilibrium. So now at that point, the box is moving. So there's a difference in when it's stretched completely all the way out versus when it's moving through equilibrium. And we're going to ask the same three questions just in a different order because it makes it a little bit easier to solve. So what's the effect of the speed of the oscillator? How does it affect the amplitude and the period of oscillation? So let's start with the effect on the speed of the oscillator as it moves through equilibrium. Well, we could try to use conservation of energy and draw our energy bar chart. We have stored spring energy, but then the moment the box is dropped on top, we know that the box that is moving is now going to lose some of that energy because the two boxes stick together. So it's going to lose to the surface of the two boxes, the friction that allows them to stick together, which means the kinetic energy is going to decrease, which means we can't use conservation of energy. So because a collision occurs and something's moving, we're going to use conservation of momentum. So we can draw a momentum bar chart. So the mass of the oscillator by itself has a momentum as it moves through equilibrium. And then we know that when the second mass is dropped on top, that it's going to have the same momentum because momentum is conserved. The reason energy is not conserved is because this is a perfectly inelastic collision. Two objects collide and stick together. Therefore, energy is not conserved. So we have to use conservation of momentum. So knowing the speed of the collision before is v, we're going to solve for the final velocity. So we can write our conservation of momentum equation. mv is equal to 2m times vf. We can cancel out the m's and then solve for the final velocity and see that the velocity is going to be half as much because when the mass is doubled. Second question, how does this affect the amplitude of the oscillator? Well, the oscillator had a kinetic energy before, we'll call that kinetic energy B, KB, was 1/2 mv squared. That was before the collision. But we know the kinetic energy after the collision is going to be different because Ka is going to equal 1/2, and we've doubled that mass. And then we just solved that the velocity is going to be half of what it was. So if we simplify this, Ka is equal to 1/2 mv squared, and then 2 divided by 4 is going to give us 1/2. So the kinetic energy total is going to be equal to 1/4 mv squared. If Kb was 1/2 mv squared, we know that 1/4 mv squared is going to be half the amount of the original energy. So now what we're going to do is we're going to go and use conservation of energy. Once the box is dropped on top, we know that energy is not going to be dissipated through the frictionless surface. So we have kinetic energy is half of what it was, so that's why we drew only 2 bars. And as that spring oscillator now goes to compression, the box is transferring energy to the spring, and it gives us the stored spring energy, which is also going to be half of what it was originally, because the energy that's lost is half the amount of the energy that it had to begin with. So now we can know that if us is equal to 1/2 kx squared, and x is the amplitude of the oscillator, well, we know that us is half of what it was originally, so half of it is, and it's proportional to the amplitude squared. The way we can make the 1/2 kx squared side half as much by changing the amplitude means that we're going to divide it by the square root of 2, because 1 over square root of 2 squared is 1/2. So that means the amplitude is going to decrease by the square root of 2. So if we look at that as an example, if the amplitude was a half a meter, it would now be 0.5 divided by square root of 2, or 0.35 meters. So the amplitude decreases. So how does dropping the box of equal mass impact the period of oscillation? Well, looking at our equation, we know that spring constant and mass are the only things that affect the period. And what we have effectively done is double the mass. The amplitude doesn't have an impact. So doubling the mass means that the period is going to be square root of 2 times longer. So if it was 1.5 seconds, it's now going to be square root of 2 times 1.5, or 2.12 seconds. So let's look at scenario 3, where we have a box that is moving, a box that's stationary, where the springs at equilibrium, and when they collide and stick together, they start to oscillate together. Both boxes again have the same mass m. The spring constant of the spring is k. And we're going to ask two questions. What is the period of oscillation for the two box mass system? And two, what is the amplitude of the oscillator? So looking at the period, we know that period is only impacted by mass and spring constant. So we know that the period of the spring oscillator is going to be 2 pi squared of 2m divided by k. What is the amplitude of the oscillator in terms of V, M, and K? So we're going to derive this. The first thing that we're going to do is we're going to use conservation of momentum. Well, because we know that the box 1 was moving and collides with the stationary box, so we need to know what the speed is in terms of that original speed, V. So we can draw our same momentum bar chart that we saw in the previous example. We have 1m moving and then it changes to 2m. We have mv equals 2mvf. And solving for the final velocity, we get that the final velocity is v divided by 2, so half of the original velocity when the mass is doubled. Now, since we know the velocity, what we're going to do is we're going to transition use conservation of energy because the amplitude has to do with how far the spring is stretched or compressed. So using conservation of energy, we know we have kinetic energy to begin with. The box transfers energy to the spring. It gives us stored spring energy, and that's going to help us figure out the amplitude or how far the spring is stretched or compressed because kinetic energy equals the stored spring energy. So we can substitute the equations in for each of the types of energy. And then we're solving for the amplitude of the oscillator. We know that x is the amplitude of the oscillator. So we're going to solve this equation for x. And we get x is equal to the square root of mv squared divided by k. And what we know is that the mass is now 2m. The velocity is v divided by 2. So we substitute those in. And we get x is equal to the square root of 2m times v over 2, that quantity squared, divided by k. So now let's simplify this. So let's go ahead and square the term. So we get 2m times v squared over 4 divided by k. Well, 2 divided by 4, that's going to be 1/2. We can bring the 2 to the denominator, and that gives us that the amplitude is the square root of mv squared divided by 2k. So the amplitude of our oscillator can be calculated in this way because the amplitude is just going to equal that mv squared divided by 2k and the square root of that quantity. So this is an introduction to collisions with oscillators in 3 different scenarios. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.